Now, we are going to look at the next class of instructions. Data manip. We're not even going to spell it out. It's always manip, okay, from here on out. If you say manipulation, you fail the class, okay? Because it's not that big deal. It's just that you're not paying attention, okay? So F. F! This is the first class of instruction. This is the second. Why do we want to manipulate data? It's because that's what a computer does. It's not that fun to load and store, although you can read from switches using a load, and you could store to LEDs and repeat. So you could actually write a computer program to do that. So that would be cool, but it's only cool for a few seconds. Then it's like, what does it do anything else? It's like, do you understand how hard it was to make a computer to do that? But no, the customer's always right. We got to do something. Data manip means you're going to take information and you're going to take data and manip it. Okay? Manip it. What data? Well, let's go back and think about this. The data that we're going to manip can only be manipped by the ALU. Okay? That's our manip circuit. It's a circuit to manip. Manip a circuit. Manip a circuit. Manip a circuit. Okay? You follow me? You shouldn't. You know what the ALU's inputs are? They're A and B. So if you're going to manip, you need to have the data in A and B. So what a manip does is it takes A and B and it does something. Types of manips we can do: add A to B, negate A, negate B, subtract B from A, take the 2's complement of A. Okay? Now here's something to think about. When I do this, I take A and B and I go through the ALU. But then the answer comes out. What am I going to do with the answer? There's not enough time to write it to memory because the ALU is a combinational logic circuit. It's going to compute the information, produce a result, then as soon as you mess with its inputs, it's going to change the result. So we need to take that information and within the execute process, put it somewhere fast. Where is the only place that we have fast storage in our computer? It's the registers. So what you see when you have data manipulations in a CPU, it's stuff like this. It's A plus B, then put the sum back in A. So that's what we do. We use A and B as the inputs, but we put the output back in one of the registers. Then if we're going to do 2's complement of A, it would be like A gets 2's comp, I'm not sure if there's an operator or something, of A. Something like that. I just made that up. That's pretty cool though. Not going to lie. All right? So does that make sense? Okay. Life is good. I walk up to you and I say, let's just do a fictional data manipulation instruction. Okay? And let's do this. I would like to add A to B. Now this one's going to be really simple because we're not at a level where we're even looking at data routing. What addressing mode does this use? Don't look up there. I know it's up there. Okay, I got this projector, and you're like, why can't I look? Don't look. Okay? Everybody's looking. Have you noticed that? You want someone to look at something? You know what you do? Tell them not to look. What? Don't look over there. What? Poke your eyes out. Where? I need it. What is an addressing mode? How to treat the operand, whether it's data or an address. Do I need an operand for a data manipulation? Not this one. You know why? Because the inputs to the manipulation are already in the CPU. The output of the data manipulation will be in the CPU. All we need to do is tell the CPU, hey, you got some information, add it together and stuff it back into your own registers. Okay? So that's all we do. There is no address, or there is no operand. That means the addressing mode is what we call inherent. The opcode itself, what you do is inherent within it. Within that single code, which I'm going to just randomly assign 4.2. Okay? If you read 4.2, you know you're going to take A, add it to B, put the sum back in A, and that's it. you don't have an operand. Everything you needed to know was inherent in the opcode. Does that feel good? All right, all right. I walk up to you and I say, why did I choose 4-2? Random, it's what they do in 371. If my prior instruction was a good instruction, which it was, program counter is equal to 0-4. It is already pointing to the location of memory, which is the opcode. I know that I'm ready to go fetch the opcode. So what do? I need to put out on the address bus. Look at that. Wrote that backwards. Kind of scary. Don't think about it. Okay? That's what I do. 0-4 is going to go into the MAR. Does that feel good? Because that's where I'm going to go get the opcode. So I got myself a 0-4 on the address bus. That means out here, it's going to grab the opcode. The opcode is coming over to the CPU on the data bus. Okay? What should I do with our buddy, 4-2? It's an opcode. It's going one place, the instruction register. So it's going to come over to here and go into the instruction register. Now the reason I'm drawing this as enter from the left, exit from the right of these registers is because that's how you're going to conceptualize it when you code it up. It really is in on the left, out on the right. Okay, now instruction register has 4-2. I fetched it. Oh, have I fetched completely? There's nothing worse than a half fetch. Let's do a full fetch. What is left to full fetch? Say full fetch a bunch of times. You could spit all over the lens here. Oh, that's gross. Don't do that. 4-2 is in the IR. What else do I need to do? Update the program counter. You know, I'm going to step backwards. Update? Let's say increment. Can we? Thank you. I'm going to increment it because then it's going to point to the next location in memory, which I have no idea what it is. It could be an opcode. It could be an operand. How do I know what it is? Decode. It's time to decode. I go up and I look at 4-2. 4-2 is now sitting here and I'm looking at it and I know the following. I know a whole bunch of stuff. I know, number one, this is an add. I know it's inherent addressing, meaning that the inputs are A and B, the output goes into A. I also know that since it's inherent addressing, there's no operand. That means the program counter sitting at 0-5 is pointing to what? The next opcode in memory. This instruction only took 1 byte. We now have instructions that take 2 bytes and 1 byte. How are we ever going to keep track of whether it's a 1 byte or a 2 byte? With the finite state machine, exactly. Once you decode it, that dictates the path you take through the states. And if you only need to go grab one operand, then go grab one operand. If you need to not grab an operand, then don't grab it. Just go back to the fetch. Okay, I get it. You know what you do? All you do is you go to the ALU now and go, hey, go ahead and turn the adder on. It goes, vroom, and now the sum comes out of the ALU, and you tell A, hey, go grab the sum from the ALU. You go latch, and now all of a sudden, A has the sum. Now you're like, geez, that was some, you skipped over that. I did skip over it, okay? Because the details of it, you don't even need to know them right now. You know you're going to build a circuit to do that. So I ask you at this point, am I done with my instruction? Yes. I did what I came to do. I added A to B, and I put the sum in A. And the program counter is pointing at the next location in memory. Okay. How's this feel? It's a lot. You know what else it is? It's repetitive. Do you see a common theme? We're almost always doing the same thing. Okay. Put program counter in memory address register. Go read from it. That's the opcode. Increment the program counter. That is the fetch. Okay? Very repetitive. You know why we teach it in a repetitive manner? Because that's how it executes. It's just over and over and over and over. Fetch, decode, execute. Fetch, decode, execute. You wouldn't think you could ever get anything done just doing those 3 things over and over and over, because look at how long it takes to do anything. It took multiple reads, multiple reads and a write to actually just put information out to a port. It's taking a whole bunch of clock cycles to do the simplest things, to do what a wire would do. If we brought in switches and put them to the LEDs, we could have done that with wires. Why would we use a computer? Computer, we have to load from an address, store to an address, and it's just going forever and ever and ever. How are we ever able to get anything done with a computer? Because it's fast. Increment program counter. It's a clock cycle. But guess what? Those clocks happen how many times a second in a computer? Billion! Billions. Or gigahertz would be a more engineering way to say it. But billions is way better, isn't it? Isn't it? All right. At this moment, we have covered the second class of instructions.